Industrial robots. They're pretty much the backbone of modern manufacturing, right? But here's the thing. They come with this one giant challenge. To work with them, to learn about them, you've always needed the actual super expensive hardware. But what if? What if you didn't? Okay, so let's dive right in. What you're looking at here is a complete software-based simulation of a 6-axis robotic arm. It's called a cybertwin. This amazing project, built by Yuna Chang Liu, tackles that massive hardware problem head-on, basically making robotics development and security training accessible to anyone with a computer. So to really get why this is such a game changer, we first need to understand the core problem it was designed to solve. And it all really boils down to the hardware. I mean, just imagine you're trying to set up a training class for a team of cybersecurity analysts. You wouldn't just need one crazy expensive robot arm. You'd need like 10 of them. The cost, the space, the upkeep, it just doesn't scale at all. It's been a huge bottleneck for both developers and security pros for years. And this wasn't some abstract problem, you know? The creator actually ran into this exact wall with a previous project, one that used this physical Brachio Plus arm. It was cool, it worked great, but trying to use it for a big cyber training exercise? No way. Impossible. That frustration right there was the spark that led to creating a purely software solution. So how do you get around this huge hardware problem? Well, you do it with an incredibly elegant software solution, the cybertwin. Okay, this is super important. A cybertwin isn't just a video game with a robot in it. It's a functional, interactive model of a real-world system. It uses the same industrial standard protocols, it behaves like the real thing, it communicates like the real thing, and as we're about to see, it can even be hacked like the real thing.
Now, this pyramid looks a little complex, I know, but what's really cool is how it's all organized. This isn't just a bunch of random code cobbled together. It's built on something called the ISA 95 standard. You can just think of it as the official rulebook for how factories are automated, stacking everything in layers from the physical robot on the floor all the way up to the business offices. But we're going to make this way simpler.
The creator uses this fantastic analogy that just makes it all click. Think of it like a person. Level 0 is the robot's body, you know, the actual parts that move. Level 1 is the brain, the part that makes all the decisions. And level 2 is the remote control, the screen you use to see what's going on and give it commands. Body, brain, remote control. Simple. All right, so let's dig into each of those layers, the body, the brain, and the remote control, and see exactly how they work together to make this whole virtual robot come to life. So first up, we've got level 0, the body. This is the 3D simulator itself. It's built with OpenGL, and it's basically a virtual space where the robot arm lives, along with the little cube it picks up and all the pretend sensors and motors. This is where all the physics happens. It's the digital replacement for all that heavy, expensive hardware. Okay, so you have the body. Next, you need the brain. That's level 1. This is a virtual PLC, or a programmable logic controller. In a real factory, a PLC is the tough little industrial computer running all the automation. And in the simulator, it does the exact same job. It gets data from the simulator's sensors, thinks for a second, and then sends commands back to the simulator's motors. And finally, we have level 2, the remote control. This is the HMI, or human-machine interface. It's the dashboard an operator would be looking at. It connects to the PLC over the network and gives you a real-time view of everything, all the joint angles, all the sensor readings, and it lets you send commands from anywhere. And this diagram just lays out the whole data loop perfectly. The 3D simulator, the body, sends sensor data up to the PLC, the brain. The brain makes a decision and sends motor commands back down. And all the while, the HMI, the remote control, is talking to the brain, letting a person watch over and control the whole shebang. It's a perfect digital mirror of a real industrial setup.
So let's make this super concrete with the auto grab function. When you click that button on the screen, this whole chain of events just kicks off instantly. First, the PLC reads the cube's position from the simulator. Then it does a bunch of math to figure out all the right joint angles. Next, it sends a whole sequence of commands to the motors to make the arm move. And finally, it tells the gripper to close. The whole system working together in perfect harmony.
Now, look, creating a simulator that's this realistic is already seriously impressive, but its most powerful use case, that comes from putting it under pressure, and I mean real pressure.
So think about it. You've built this perfect digital twin of an industrial robot. It looks real, it acts real, it even talks over real industrial networks.
how do you prove its value? How do you really, truly put it to the test?
You let people hack it. That's right. This cyber twin isn't just some side project. It's the actual foundation for challenges in huge international cybersecurity competitions like the CISS 2024 Capture the Flag event and Germany's Best Hacker. The contestants have to find real vulnerabilities and take control of this virtual robot just like they would a real one on a factory floor.
And this is why this project is just so important. It creates the perfect training ground for securing what's called operational technology, or OT, the tech that controls our physical world. You can launch real attacks in a completely safe sandbox. You can analyze industrial network traffic, you can test security tools, all without any risk to physical equipment and without spending a single penny on hardware.
So let's just pull back for a second and look at the big picture here. What's the real takeaway from this incredible project? This quote from the project summary just says it all. This is not just some cool 3D model. It is an accessible, hardware-independent platform. It lets developers build better control systems, and it lets security professionals learn how to defend our most critical infrastructure in a way that just was never possible before.
And that kind of leaves us with a pretty fascinating final thought. As our world relies more and more on automation, in our factories, our power grids, our water systems, the risk of cyber attacks just grows every single day. So could hyper-realistic, accessible virtual sandboxes just like this cyber twin, could they actually be the key to training the next generation of defenders? Could this be our most important line of defense? It's definitely something to think about.